Hello and welcome to this introduction to NMR spectroscopy. This is where we're going to learn a little bit about a really important tool that we use in the laboratory as a way to identify, characterize a compound that we've maybe synthesized or isolated. And there's really no better way for structural elucidation for small molecules than NMR spectroscopy. So like all spectroscopies, it is the tool we're using is we're using light to interact with our molecule, with our sample some way. So if we take a look at the electromagnetic spectrum, we'll see that all sorts of different types of light energy are used for structural analysis or just analytical tools. Of the electromagnetic spectrum, the region that human beings are most familiar with is the visible range, because that's, of course, the part of the spectrum we can observe visually, we can see with our eyes. And so you might remember the colors of the rainbow, that Roy G. Biv acronym. We have red, orange, yellow, green, blue, violet. And so that is the range of wavelengths that we can see in the visible range. And then just outside of the red region is where we have the infrared region. Just outside of the violet is where we have the ultraviolet region. And this is just one small part of a long continuum of the spectrum of light. And so you could see that we have a representation here of the wavelengths that are associated with this, kind of what's happening. And we can also see that we can also observe that the energy is changing with those wavelengths. So as we move from violet to red, and then continuing on to the microwave region and into the radio region, what looks like is happening with our wavelengths. Our wavelengths are getting longer in this direction. And what is the energy of those? As we have a longer wavelengths, those are going to be lower energy radiation. If we go in the opposite direction from the visible range, we get the ultraviolet light, and then the X-rays, and then even eventually gamma rays. So are these things you would associate with low energy radiation? No, these are definitely higher energy radiation, because we have much shorter wavelengths. So when you think about sunlight, the visible light that we have there, the parts that we can't see are the infrared region that's coming from the sunlight. That's the part when it touches our body, it feels warm. So that's the part of light that kind of heats things up. And on the other end, we have the ultraviolet. That's the part that of sunlight that causes skin damage, that causes sunburns, that can cause skin cancer. So definitely higher energy, more destructive. And of course, X-rays. If you've ever gone in for an X-ray, they put lead blankets over all your private parts, making sure to minimize your exposure to X-rays, because it's so damaging. And what about gamma rays? How high energy are those? Now we're talking like the Incredible Hulk, right? that's where you have those could be lethal. So so anyway, just the wavelength is one feature of this light energy. We could also talk in terms of frequency. Frequency is inversely proportional to the wavelength. So something with a I'm sorry, I take that back. I'm mixing my things up. If we have a very long wavelength, then if you're thinking about the frequency by which a wave passes by a certain point, that's also going to be a low frequency, and something that is a high energy wavelength. High energy light with a short wavelength has a much higher frequency. So this is high frequency light, and that's the relationship there. So a shorter wavelength has a higher frequency and is a higher energy. So what are some of these wavelengths that we use in the organic chemistry laboratory? You might be familiar with some IR spectroscopy. That's when we use infrared light. And that is something that's used to analyze functional groups that might be present in your compound, what happens when a molecule absorbs infrared light. It results in molecular vibrations. So we have like bond stretching, we have bond bending, and so on. And you know, the energy of light that gets absorbed depends on the type of bond that's getting absorbed, and therefore the functional group. So for example, a carbonyl, a CO double bond is called a carbonyl, that has a very strong absorption of 1700 wave numbers, reciprocal centimeters called wave numbers. And what happens when it absorbs that is the carbonyl stretches. It gets longer, it gets shorter, it gets longer, it gets shorter. So if we look at something like a water molecule, that will also absorb infrared light, and some of the motions that can, vibrations that can occur when it absorbs light can be bending. So like, for example, if these two, that bond angle compresses and expands, so those hydrogen atoms get closer to each other, we would describe that as bending motion. Or you could have stretching, and the stretching can be either symmetric, where the two OH bonds are getting longer at the same time, or they can be asymmetric, where as one gets shorter, it compresses, the other one is getting longer and it stretches. So these are the kinds of things that we look for in the IR, where certain absorptions we describe as stretching frequencies or bending, and symmetric and asymmetric. You've probably heard of those terms. Okay, so what do we do with NMR spectroscopy instead? Now, instead of using infrared light, and by the way, UV vis spectroscopy is a huge area of you know, analytical techniques, and that's using this, you know, these regions of light. So that's what we find. Of course, if you have a colored compound, you could use UV vis spectroscopy to analyze which wavelengths it's absorbing, and so on. But when we come all the way out here to the radio wave frequency, so very, very low energy waves, wavelengths, we can, that's what we use for NMR spectroscopy. And so what happens is we take our sample, we put it into an NMR tube, it goes into a spectrometer, which is a giant vessel that has a magnet in there, really high powerful superconducting magnet. And so it has it's so big because it requires all of these really super cold, it needs to be extremely cold, so liquid helium is used, liquid nitrogen is used to keep it super cold. And we have different strength magnets that can be used, and so that makes your NMR instrument more expensive because it is more powerful, it is more sensitive. And so we have some NMRs that can actually be used at room temperature. They could be on a bench top, and others, you know, that are very sensitive and have very powerful magnets. So what is the magnet doing? When we put a sample in a magnet, what happens is the nuclei of our atoms, of certain atoms, are going to align with the external field that is being applied by the magnet. So our spins, nuclei can have a spin, just like an electron can have a spin, a nucleus can have a spin. We describe them as alpha and beta, and they're all just kind of random, but when we apply an external magnetic field, they all end up aligning in that direction. Now they can either align in the same direction as the field, or they can align in the opposite direction of the field. So we describe those spin states as alpha or beta. And you know, they're roughly equal in their distribution, their population, with a slightly larger population of the ones that are aligned with the field, the alpha, because that is a lower energy spin state. So once we have all of these nuclei that are in the magnetic field and aligned, we pulse it with the radio wave energy, and what happens is that energy can be absorbed, and the result is a spin flip, is how we describe it, a spin flip. and we can flip the alpha to the beta state being higher energy. And then after it has been excited, then we let it relax back down. So the energy is going to be released. We describe this process as the relaxation stage. And as it goes back down, this is how we end up observing, a signal. So the energy difference here between the alpha and the beta state, this energy varies with the strength of the magnetic field. So when you have a stronger field, that's a bigger difference. And so we're able to get much better resolution because we're able to distinguish, two nuclei that are maybe very, very similar otherwise. What is it we're looking at? We're looking at protons. Okay, so that we can look at actually several different nuclei. The one we're going to be exploring today is described as Proton NMR or 1H NMR. So we're looking at typical hydrogen atoms, which have has the mass of 1, atomic number of 1. And but you can also have C13 NMR. So of course that is very important in organic chemistry because we're studying organic molecules. So C13 nuclei can be observed, and also certain other ones such as nitrogen, phosphorus, and fluorine. So what's special about these is these are the ones that have a spin quantum number of 1/2, which means they have this behavior of acting like a tiny magnet, and when you apply the external magnetic field, they do that alignment. So not all nuclei do this, just certain ones. Luckily, protons do, and of course, our organic molecules have tons of protons all over the place, and only the isotope of C13. So C12 is the most prevalent isotope. C13 accounts for only about 1% of the carbon atoms, and so we're able to just look at a sampling of the carbon atoms, which makes that technique very interesting as well. Let's take a look at some spectra to see what these look like in practice. So what is an IR spectrum? It looks something like this. This is discussed if you're using the Klein textbook. That's in chapter 14. And so what we're looking at down here is wave number. Typically, so the units here are reciprocal centimeters, and over here we're looking at percent transmittance, percent transmission, and so this is our baseline is right up here. So if our sample, we pass a beam of infrared light through our sample, and if no light gets absorbed, if there was no sample, if it was just a blank, then it just goes straight through, and we get 100% transmission, or some amount close to 100%. So nothing happens. But every once in a while, our sample will have a certain functional group, which of all these different energies of infrared light, this certain one corresponds to the energy it takes to stretch the bond or bend the bond and so on. And so that's when we get these absorptions, which we can describe as, we often describe them as stretches, just because that's the motion that it is associated with. So for example, this signal here, this very broad signal, this is a broad signal somewhere around 3,300 reciprocal centimeters. That's the absorption that is characteristic of an OH group. So the OH bond stretches at that region, and because it can hydrogen bond, it has this really characteristic broad shape. Okay, this is 3,000 right here, and that's an important area for the IR, because if we see peaks just below or just above 3,000, that is characteristic of certain types of CH bonds. And so this one here, this little group of signals of absorptions, these are characteristic of sp3 hybridized carbons with hydrogens on them. So this is a CH stretch. Some of these are symmetric, some of them are asymmetric, and we can have all sorts of different, sometimes you have CHs or CH2s or CH3s. So that's why we have a variety of absorptions that often occur in this region. But that's usually where we find them, just below 3,000. okay, and so on. This region is described as the fingerprint region because there's a whole bunch of low energy absorptions and motions that are happening here, bendings and wigglings and wagglings and so on. And so they call it a fingerprint region because it's actually so complex that it ends up being unique to a particular organic molecule, just like a fingerprint is unique to a human. So so we can use computers to analyze that fingerprint region and analyze the sample and actually identify it as something if it's a known compound that we have in a bank, a spectral bank. Now, Proton NMR and C13 NMR are the two most common ones that we'll encounter. The C13 is really quite simple. And what you can see here is this is the most common C13 experiment that we do, where every single signal that we see just shows up as a single line, as just a simple single line. And this it's what this is going to tell us is how many different types of carbon atoms do we have in our structure, and it will also indicate whether each carbon is in an electron rich or an electron deficient environment. So that's what's going to tell us, depending on where in this spectrum the signal occurs, that's going to tell us what type of electronic environment it's in. So the ones that are way to a higher ppm, this is in parts per million, or the units that we have for NMR spectroscopy. When a carbon or any other nucleus is an electron deficient region, if something is causing it to be electron deficient, we describe those carbons as being de-shielded, and then they occur towards the left at a higher number. And if they are electron rich, if they're an electron rich environment, they are described as being shielded. Such carbon atoms or protons are described as being shielded, and they come closer to zero. Now, there are other terms to describe this region of the spectrum. When it comes further to the right, these are described as more upfield signals. When it goes more to the left, this is described as downfield, the downfield region of the spectrum, which of course is totally counterintuitive, because as you're going upfield, your numbers are going down, your parts per million are going down. So that always frustrated me as a student. So what I did to solve this problem is I pictured a little triangle, a little hill underneath the spectrum, so that I said, okay, as I move towards zero, I'm moving up this ramp, so that is the upfield region. So if we say that this signal went from 50 to, something cause it go from 50 to 100, we describe that as a downfield shift, because it's going to a higher number. So hopefully this little trick will help you make sense of it, like it did for me. Okay, so I will talk a little bit about C13 NMR. We'll do some time analyzing those, but primarily the biggest thing, and actually I can mention it super quick, because there's really three different regions that we want to look for when we see carbons that occur somewhere in the 200 region, around there. That is where we're going to find carbonyls. So a CO double bond ends up the furthest downfield, the highest number, usually all the way down around 200. When we have things that are kind of in the 100 to 150 region, that's where we have sp2 hybridized carbons. So if a carbon is on an alkene, carbon-carbon double bond, or maybe on a benzene ring and an aromatic ring, that's where they would show up. And all the others are down here. So these would just be the ordinary sp3 carbons, tetrahedral carbon atoms. So we could tell that, well, that's very general information we could get from C13. Okay, but when we look at the Proton NMR, it is so rich with information and data that it takes a little while to learn all the bits and pieces and how to interpret them. But more importantly, it tells us how to it will give us a precise structure. We'll be able to use Proton NMR to actually not just say, like IR says, oh, it's some kind of alcohol. Like, that's great. I don't know which alcohol, but I know it's an alcohol. It has an OH group. We're now going to be able to use Proton NMR to come up with an actual structure, an exact structure for even for very complex molecules. It's really an amazingly powerful technique. So this is what a Proton NMR looks like, and so you could see our range of numbers now. It's still in ppm, but compared to carbon, it's much smaller. It's usually in the range of 0 to 10, and so on. And furthermore, each of our signals here is not just a line. It's going to be split into multiple lines, and so we describe it as a multiplicity, or having some kind of splitting pattern. So that's interesting as well. Sometimes we see a signal right at 0. It might occur in the spectrum. If it does, that is not part of our structure. That's just a standard that was added to the sample so that we can kind of use that for reference. That's not often done anymore. But the reference we use, the definition of these parts per million, is parts per million with reference to TMS, which is tetramethylsilane. Tetramethylsilane is defined as being at 0, and then everything else is relative to that. And this is the structure of tetramethylsilane. Silicon on the periodic table is right underneath carbon, which makes it one of the very few elements that's actually less electronegative than carbon. Less electronegative, meaning that carbon will pull electron density away from silicon. So or you could think of the silicon donating its the electrons from these sigma bonds are very polar in the direction of the carbon, which is really unique and very different from most organic molecules. And so that makes these carbon atoms unusually electron rich, partial minus. These are very, very extremely electron rich hydrogen atoms, protons. We call them, we always describe them as protons in spectroscopy, but we're talking about H atoms. So these are very, very electron rich protons. And what happens when you're electron rich? They shift upfield. And so this is pretty much the most electron rich CH you're ever going to encounter when you analyze the spectrum. And so that's why if we set that to 0, then everything else we see is going to be to the left of that. It's going to be downfield of that. Again, usually from 1 to about 10. Can you have samples with negative ppms? You absolutely can, but they're very unusual organic molecules and not the type that we're typically going to encounter in our course. Okay, so what is it that we can look for in an NMR? What is all the data we're going to be exploring in the NMR? The very first thing is the number of signals. So how many different resonance signals are we going to see here? And oh, I should say, by the way, what does NMR stand for? I jumped right ahead on that. So that's nuclear magnetic resonance. We're using a magnet to study the nuclei. And we could describe this this spin flipping as undergoing a resonance, and it's actually an interesting, it's an important technique that we use not just in the organic chemistry lab, but if you've ever had the pleasure of getting an MRI taken of a various body part, you have an injury of some kind, you're actually undergoing an NMR here. It's like you're a big NMR sample that they slide into this tube, and they use a magnetic field, and they do this exact same thing. And what are they observing? Is they're observing the protons that are in the water molecules. So MRI is used for soft tissue. X-ray is something we could use to see bones, and NMR is something you could use to see soft tissue. So you could, if you have a muscle tear or something like that, you can visualize that better using MRI technique. They don't call it an NMR because that actually would sound a little scary. If I'm going for a nuclear test, that might freak people out. And so it has a different name for when it's used for medical purposes. And they instead call it magnetic resonance imaging, MRI, but that's the same thing. So yeah, each of these organic chemists typically call these signals, although that's kind of complicated because they're not really signals. So I think the more precise term is to call it a resonance. But so the number of signals that are showing up here, or resonances that are occurring with this particular sample, will tell us the different types of hydrogens we have. How many different kinds of protons are there? And for that, we're gonna talk about, like, well, how do you decide that certain protons will be equivalent to each other? So for this example, we have 1, 2, 3, 4, 5. There's 5 here in this particular in this particular spectrum. The next thing, one other thing we could look at is the integration. The integration is the area under each peak. So the instrument is going to measure the area under these 4 peaks and add them up. And that peak area is called the integration. It tells us how many hydrogens are in each signal. And so it's going to be given as a ratio. So is there 1 H of that kite, or 2 hydrogens, or are there 3, and so on. The chemical shift is what we call the ppm. So this it's also known as a delta value. So these numbers, in this case, the kind of from 1 to 4 are the various chemical shifts. They're called delta values. And they're given in parts per million. Again, usually they're lower than 10 for proton NMRs, for proton NMR spectra. And what is this telling us? Like we already mentioned, it's the electronic environment. So are we looking at protons that are more electron rich, or are they more electron deficient? That's what's going to tell us where on the spectrum it's going to occur. We call that the chemical shift. And then finally, we have the splitting pattern. The splitting pattern, also called a multiplicity. Sometimes you're going to have it described as a multiplicity. I think it's just a lot easier to describe it as a splitting multiplicity. Thank you. The splitting pattern. So how many, instead of, sometimes it's just a single peak, we call that a singlet, but sometimes it's split into 2 or 3 or 4 or more. So for example, this signal would be described as a triplet. It's called a triplet because it has 3 peaks to it. And there's a few other triplets. This one is also a triplet. It has 1, 2, 3. And this also is a triplet. Notice the triplet is always going to have this kind of same pattern where we have 2 smaller peaks and then 1 middle peak that's much taller, right? So those are called triplets. Over here, this would be described as a quartet. As a quartet because it has 4 peaks. That's its multiplicity. And this one down here, what do we have? When we blow this up, we see we have 1, 2, 3, 4, 5, 6. So this is called a sextet. This is called a sextet. So we'll look at singlets and doublets and triplets and quartets and so on. Now, what information does that tell us? Why sometimes do we have a doublet and sometimes we have a triplet? What this tells us is the number of neighboring protons. So this is now going to help us link this CH with this CH and start to put the pieces of our puzzle together. The size of the distance between the peaks is called the J value, and it's called a coupling constant. When these 2 protons are causing each other to split, we just describe them as being coupled. And where does that number come from? It depends on the spatial arrangement between those neighboring protons, more precisely the dihedral angle. And so sometimes we have very, very small J values. Sometimes we have very, very large J values. Usually they're just kind of averaged out to somewhere in between. But anyway, we're going to step by step slowly explore each of these 4 areas so we understand the theory behind them. And then the important part is we're going to now then apply them. How could we first, how can we predict a spectrum from a given compound, know what the spectrum would look like, and then the bigger task after we really become familiarized with NMR, what the components of an NMR spectrum, then we'll be ready to do the last part, which is to take an NMR spectrum like this and propose a structure that is consistent with that. So we're gonna break the lesson. This is kind of an introduction to NMR. Now, next we're going to dive into these 4 parts and the theory behind it, and predict spectrum. And then the last part will be predicting spectrum. So I'll see you for the next part.